If your AI model had a brain, its key-value cache would be like a library assistant who remembers every word ever said in every conversation. Imagine an assistant who stores not just the book, but every single page in full illegible handwriting, using 60-80% more space as filing gear than is actually needed. That's exactly what's happening with LLM inference today. That's why Google Research's new algorithm, TurboQuant, is beginning to rethink how we think about AI memory. Presented at ICLA 2026 and published on Google's own research blog, TurboQuant compresses the KV cache by 6x with zero accuracy loss. Not a fix, not a near miss, zero, nothing. If you followed our AI Learner series Article 7 on KV cache, you know what's happening here. The cache is the first-rate bottleneck in large language model inference. As context windows push to 128K tokens and beyond, the KV cache grows linearly. Supposedly, a single 128K token, prompt on Llama 370 billion, consumes roughly 40 gigabytes of memory for KV storage alone. That's the entire capacity of an NVIDIA A140 gigabytes. Let's take this apart, piece by piece, like you disassemble a complicated wall clock to figure out why the second hand is spinning backwards. TurboQuant begins with what sounds like a mathematics trick, random orthogonal rotation. Imagine an arrow pointing north-northwest, north-northeast, then a wire dragged around to east. Now it points somewhere but is still the same length. What does this do? In TurboQuant's world, before rotation, some data coordinates carry way more information than others, the so-called outlier channels problem in naive quantization. After rotation, every coordinate follows a predictable statistical distribution, approximately Gaussian. Every coordinate as equally important, every coordinate as equally compressible. The rotation matrix is generated once through algorithm decomposition of a random Gaussian matrix and reused for all vectors. Negligible computational overhead, just a clever spin that makes everything equal. Words have weight in AI models. Some carry more information than others. The issue is that normal quantization methods can't deal with this inequality without adding overhead. Here's where TurboQuant gets supercolor powers, polar coordinates. Instead of distances along x and y, TurboQuant internally converts the data to polar coordinates, a radius signifying how strong the core data is, and an angle indicating the data's direction or meaning. Because the pattern of angles is known and highly concentrated, the model no longer needs to perform the expensive data normalization step. At 3 bits, each coordinate maps to one of 8 optimally placed buckets. At 4 bits, 16 buckets. The key insight, here's why it works. TurboQuant adds 1 additional bit per coordinate, using the quantized Johnson-Lindenstrauss transform. This acts as a mathematical error-checking mechanism that preserves distance relationships between vectors critical for attention score computation. This extra bit is what makes TurboQuant different from basic quantization. It's not just compression, it's compression with mathematically provable accuracy. On NVIDIA H100 GPU, 4-bit TurboQuant delivered up to 8x speedup in attention logic computation compared to 32-bit unquantized keys. Long bench at 5 bits, TurboQuant achieved an average score of 50.06, identical to the full precision 16-bit baseline of 50.06. Even at 5 bits, score dropped only to 49.44. Needle in a haystack up to 104K tokens context, TurboQuant scored 0.997, functionally identical to full precision. Attention throughput, 8x speedup on H100 GPUs. Recall, optimal performance across all benchmarks tested. Models tested, Gemma, Llama 3, 1 Mistral and others. This isn't about compression for compression's sake. TurboQuant remakes who can run large language models, how long a conversation they can handle, and what it costs to run them. Here's why. 1. Democratized agents. Remember how AI agents struggled with token contexts and cache out of memory in long multi-step tasks? TurboQuant makes 128K by 128K and beyond accessible for much less. 2. Cost reduction. For inference providers, every KV reduction is direct profit. TurboQuant means you can handle 4 times as many concurrent users on the same hardware. 3. Longer context for everyone. With accurate performance up to 104K tokens on second-generation models, we're looking at a future where full book analysis is not a premium feature. 4. Training-free and model-agnostic. TurboQuant requires no calibration data and no fine-tuning. It works on any transformer architecture. You don't need to retrain your model, you just switch on the compression. TurboQuant requires no model retraining and works on any transformer architecture. Community implementations are already spreading, open source ports are on the way. If you use LLM or other inference engine, watch for TurboQuant built-in as a drop-in optimization. TurboQuant is like finding a filing cabinet that organizes itself, takes up less space, and somehow remembers everything better than before. It's a reminder that sometimes the breakthrough isn't a bigger brain, it's a smarter way to file what you already know. In a world racing toward trillion-token contexts, efficiency isn't optional anymore, it's the whole game, and Google just changed the rules. 1. What is the KV cache, and why does it matter for LLM inference? 2. How does TurboQuant's polar coordinate approach eliminate the need for expensive normalization? 3. Why is TurboQuant described as training-free and model-agnostic? 1. The KV cache stores key-value pairs for every previous token across every attention layer during inference. It grows linearly with sequence length and becomes the primary memory bottleneck as context windows push to 128K plus tokens, consuming up to 40 gigabytes on a single 128K token llama 370 billion prompt. 2. TurboQuant converts coordinates to polar form, radius, and angle. Because the angle pattern is known and concentrated, the model no longer needs expensive per-block normalization. This maps data onto a fixed, predictable circular grid where boundaries are already defined. 3. TurboQuant requires no calibration data and no fine-tuning. It works on any transformer architecture by using mathematically optimal quantization buckets derived from probability theory alone. You compute them once and they work on any model, no retraining needed.